Greetings, geometers. Today, on this lovely day, we are going to use the properties of special right triangles to find missing sides. Now, the nice thing about special right triangles is that it's all derived from our friend, the Pythagorean theorem. What we're going to find is that when we use the Pythagorean theorem under two contexts, that is a 45-45-90 triangle, so just to give more context there, that looks like this, where it is an isosceles right triangle, like so. And this angle here is 45 degrees, as is this angle here. So it's called a 45-45-90 triangle. You could call it also an isosceles right triangle. The next one is a 30-60-90 triangle. And this one's actually a special one because when you take an equilateral triangle and slice that puppy in half, then we end up getting a 60-degree angle there, a 30-degree angle there. Hence, we get a 30-60-90 triangle. And this has a very special relationship, too. So, by way of background information, we need to know how to simplify radicals. And the way that we do this is we're not allowed to have a radical down in the denominator. So all we have to do is multiply the denominator by itself, and that should be a 2, square root of 2. And then whatever I multiply downstairs, I multiply upstairs. So 3 radical 2 all over 2, because radical 2 times radical 2 is positive 2. And that's how it simplifies. And in the second problem right here, we multiply by radical 3 in the denominator, in the numerator. So I get 3 radical 3 in the numerator and 3 in the denominator. Notice that the 3 outside here and down here reduce. So I end up with just simply radical 3. So sometimes we reduce, like here, and sometimes we don't, like here. And this one here, we multiply by radical 3 in the numerator denominator. 12 radical 3 all over 3. And now the 12 and the 3 reduce to be 4 radical 3. And there we go. So that's going to become very helpful in what we do momentarily. Now I'm going to do this first one here. You can do the rest with practice. But I will just jump to the answers for this. So here we're told that we have an hypotenuse x here. So that's my c. So we know that if I use Pythagorean theorem, a squared plus b squared equals c squared, then I'm going to put the x over in this side here. And then the 10 squared plus the 10 squared there. Well, the 10 squared simplifies here to be 100. And now the hundreds add up to be 200 x squared. And when you square root both sides, you get 10 radical 2. If you need to see where that comes from, it looks like this. The square root of 200 can break up to be 100 times 2, and then a 10 times 10. And remember, the rule is whatever repeats comes out, and whatever doesn't repeat stays in. So 10 radical 2. So notice here, if you have a side length 10 and a side length 10, 10, 10, 10 radical 2. So just to jump to the answers here, 3, 3, 3 radical 2. 5, 5, 5 radical 2. So there's a rule to be seen there. The next one is a 30-60-90 triangle. And let's clarify here that x is also the hypotenuse, just like in the previous problems. So this one here is my a, 5 squared. This one here is my b. I'm going to put parentheses around the whole term because I'm going to square both. And this here is my c. So 5 times 5 is 25. This here becomes 75. Where does that come from? Well, remember when you have a cube outside or a square outside, that's like similar to the distributive property. So 5 squared times radical 3 squared. 5 squared is 25, but this here drops out, so we're left with the 3. So 25 times 3 is 75 equals x squared. This simplifies to 100, and x is 10. So notice a pattern here. 5, 5 radical 3, and 10. So what's the pattern here? 10, 10, radical 3, and 20. In other words, I double that. And lastly, 7, 7 radical 3, and 14 here. And now that we've witnessed the pattern without proving it, we can begin to conjecture what the pattern might be. In a 45, 45, 90 triangle, the hypotenuse is radical 2 times the size of the leg. Now, how does that work out practically? It's actually not overly complicated. What we always can do is if you set up a proportion, 1, 1 radical 2, this is an extended proportion, and here you put the leg length, and here you put your hypotenuse length. Again, notice that 8 and 8, your legs are the same size. So I put 8 over 1, 8 over 1, and x over radical 2. Now what's nice about this is we can either cross multiply or some other method in order to solve. Notice here to get x by itself, if you cross multiply you get x times 1, which is exactly what I want, equals cross multiply 8 times negative 2 to get 8 radical 2. And there we go. We found out what the value of x is. And another way to consider it is, since this is your leg, and to get to your hypotenuse, you just multiply by radical 2 to get 8 radical 2. Let's see that as one other example. Here, instead of having a leg size, turns out this one is x, so is this one, I have rather my hypotenuse. So I'm still going to set it up exactly the same. 1, 1, and radical 2, and I'm going to turn this into an extended proportion. Now I'm going to put the values of x here and here since I don't know what my leg is, but I do know my hypotenuse, so I'm going to place that over here. Now I'm going to solve for one of my proportions, it doesn't matter which one, and I don't need to cross multiply here. Why? Because x divided by 1 is already x. So notice how this simplifies. I get 15 over radical 2, which brings us back to the original problem where we have to rationalize the denominator, get rid of that radical down below. And so we end up getting 15 radical 2 here, and we end up getting just 2 there. Notice that these two do not reduce because 15 is not even, so I finally just commit to my answer, 15 radical 2 over 2. And now this brings us to our second type of triangle. In a 30, 60, 90 triangle, the hypotenuse is twice as long as the short leg, and the longer leg is radical 3 times as long as the shorter leg. So, if you are given the short leg here, all you have to do is double it to get to here and multiply by radical 3 to get to the longer side. So this one, or longer leg, 12 radical 3. Now, that might be hard to remember, or it might be hard to apply if you're given this or this and going backwards. So, if we remember this, small, medium, and large, 1 radical 3 and 2, and we put our small leg there, our medium side or our longer leg, and lastly the hypotenuse or small, medium, large there. So now let's see which one's small, medium, and large. The 12 here is my small, so 12 over 1 equals the medium, x over radical 3, and the large, which is y at this stage, because I actually haven't figured out the answer. Now I just need to solve something. So notice here is I can cross multiply 12 radical 3 times equals x. So x times 1 is x equals 12 radical 3. Done. So I did cross multiply on that one. Now over here, notice what I get. Here, I can actually ignore this guy right here and cross multiply with my other two, the outer fractions. 12 times 2 equals y times 1. 12 times 2 is 24. Y times 1 is y. Now let's turn our attention to another problem here, and our setup can be exactly the same. We don't even have to think too much about it. We do small, so that's 1. Medium is over radical 3, and large is going to be over 2. Now I'm just going to cross multiply, don't have to, because look, x divided by 1 is just x. So look, when I simplify, I get 12 over radical 3. Now, I do need to finish this like we did it previously. And so the x becomes 12 radical 3 all over 3. And then I can still reduce the 12 and the 3. I get 4 radical 3. Now, we're tempted maybe to now work on this right here and maybe cross multiply or take this one and double it to kill the 2 here. But you know what? I am actually going to substitute over here. We actually know what this one is. It's 4 radical 3. Now, why am I choosing to do that? Because when I ignore this guy, notice what happens. Y times 1 is y, which means all I have to do is multiply those two to get my answer. So just to rewrite it to see where things look, now when I cross multiply this, I get y equals 8 radical 3. Where did that 8 come from? 2 times 4 is 8, and the radical 3 stays with it. So now I have my 2 answers. So in review, when we have a 45, 45, 90 triangle, we use the extended proportion 1, 1, radical 2. When we have a 30, 60, 90 triangle, we use the extended proportion 1, radical 3, and 2. All we do is put our small, medium, and large, and in some cases we cross multiply, and in some cases we don't. This will always work for every 45, 45, 90 and every 30, 60, 90 triangle.